Before we start talking about permutations and combinations, let's just get a little bit more comfortable looking at different ways of counting things. So let's take a look at this first problem here and just start going through some of these scenarios. Determine the number of ways that a computer can randomly generate each situation. So in the first problem, we've got a situation where we have two integers from 1 to 10 whose sum is 6. So what we're trying to figure out is what are the number of ways that a computer could randomly draw or randomly generate two integers that range from 1 to 10 that when we add them up, they add up to 6. And it's okay to have repeating numbers. So for the first integer, let's consider all the possibilities. Since our sum is 6, we can say that the first integer can be numbers from 1, 2, 3, 4, 5, and 6. What about for the second integer now? The second integer, well, if the first number is 1, then the second integer has to be 5. That way that when we add these up, our sum is 6. Well, what about the second integer? Second possibility. Well, when the first integer is 2, then the second integer has to be 4. And you can see where this is going. Then this would be 3, this would be 2, and you know what? I went ahead and I did 1 extra because we got to have integers from 1 through 10, so I can't include 6. So sorry about that. And here we would have 1. So these are all the different possibilities that we have here. We could have 1 and 5, 2 and 4, 3 and 3, 4 and 2, and 5 and 1. So we have a total of 5 different ways that this could happen. Okay? Let's look at another possibility or another scenario. What about two distinct integers? And what we're saying here, by the way, when we say distinct, is meaning that the numbers can't be the same. Okay, we can't have something like in the previous example, 3 and 3, where those were repeating numbers. But this time we want to make sure that we have two distinct integers from 1 to 10, this time whose sum is 10. So we can have the same pair but not the same number. So the first integer, and let me make sure I write that here. We can have the same pair but not the same number. Okay, so again, that means we can't have something like a 3 and 3. All right, so the first integer, we can say our numbers would be 1, 2, 3, 4, 5, 6, 7, 8, 9. The second integer would have to be, if the first number is 1, then the second integer would have to be 9, and we just go down the line this way. 8, 7, 6, 5, oh, and this is where we have our first issue, right? Here we see that because both numbers are 5, we're not going to include that. So when it says no repeats, that's what it's referring to here. We can have a 6 and a 4. Again, we're going to treat that differently as a 4 and a 6, because in that case, the first number or the first integer was 4, and in this instance, the first integer is 6. We have 3, 2, and 1. So how many ways do we have here? We have a total of 8 different ways that this can happen. And this process of counting the number of ways that an event can occur, that one event can occur and then another event can also occur, is called the fundamental counting principle. So if one event occurs in m number of ways and another event occurs in n ways, then we would say that both events occur in m times n ways. Okay, so the number of ways that the first event and the number of ways for the second event to occur would be m times n. All right, that word and, the fact that it is underlined there, is pretty important because that means we're going to go ahead and we are going to multiply when this is the case. Okay, so let's try this in an example. All right, so this is kind of the general idea for us to be a little bit more efficient with this. So let's look at the number of outcomes in the sample space for rolling two 6-sided dice. So we don't have any conditions about their sum or anything. We're just looking at the number of ways that we could roll two 6-sided dice. So dice number 1, I always forget this. I don't know if I'm supposed to be saying die or dice. I think it's die, I want to say. Or maybe that's the plural. Anyway, maybe I'll actually open it up for the comments if you actually happen to remember which one's which. Or, you know what, you can just Google it. All right, so dice number 1, or die number 1. Dice number 1. We've got 1, 2, 3, 4, 5, and 6. Okay, so we have a total of 6 ways that we could roll dice number 1. Well, what about dice number 2? What are the ways that we can roll that one? Well, same. They're 2 of the same dice, right? Or the 2 dice are unremarkable in that they're both going to have 6 faces, each with a number ranging from 1 through 6. So we've got 6 ways. So if we roll them together, then what we have here is we would say, using the fundamental counting principle, 6 times 6 is equal to 36. There's 36 possible outcomes. 36 possible outcomes in our sample space. And what this does is it does a lot of the mental heavy lifting for us. Like, we could go ahead and say, all right, we could have this first 1 matching up with this 1, this 2 matching up with the 1, this 3 matching up with the 1, this 4 matching up with the 1, and so on. Excuse me. So that would give you 6. And then if we move on to the next row, we could then say, all right, well, how about when this 1 matches up with this 2 matches up with the 2, this 3, this 4, this 5, this 6. And if we go down the line, we're going to have 6 different sets of 6 occurring there, which is what the fundamental counting principle allows us to do pretty efficiently. Just to count the number of ways that the first event can occur, the number of ways that the second event can occur, and just go ahead and quickly multiply to find out the total number of ways that the 2 events can occur together. Let's try another problem with that. How many possible 3 number combinations are there for the lock on your locker? Now, in order for you to do this, you probably kind of have to have a sense of what a lock looks like. There are a total of 40 different numbers that are possible for a standard locker. It usually goes from 0 to 39. So 0 can be a number. So the first number can be any number from 0 to 39, which means the first number, there are 40 different possibilities for that first number. Well, what about that second number? Now, there's nothing that says that your locker combination or your lock combination can't be 3 of the same numbers. So just because you choose one number for your first instance doesn't mean you can't use it again. Like, your locker combination could be 1, 1, 1. That would be a terrible combination, but it could be, right? So we would also say that in that second number spot, you could have 40 different numbers there. And finally, in the third locker number spot, right, you could also have 40 numbers there. So this is pretty easy to multiply. Here, we would just do 4 times 4 times 4, which is 64. And then we would say that there are 64,000 possible 3 number combinations. I'll just say combos, right? And again, this is an instance where repeats are okay, right? I'm going to write that. Repeats are okay, right? We could have something like 1 and then a 2 and a 2. That's fine. Well, what about when we don't want repeats, where maybe the condition is you can't have any repeating numbers? So repeats, not okay. How about something like this? Well, starting out with the first number, okay, for the first number, we would still have 40 different possibilities there. But because now repeats are not okay, as soon as you use a number in the first spot, that is off the table. We can't use that anymore. So now, in the second number spot, we would say there's a possibility of 39 numbers that could fit in that spot because you can't use the same number again. And once that unique number is used, then that means now in the third number spot, you're going to have only 38 possibilities. So if we calculate those, we should have 59,280. Okay, so that's how many we have there in that spot. Now, let me do one more situation, and this is maybe something that you can try on your own. What if you had a problem that asked you for something where at most 2 numbers are the same? At most 2 of the numbers are the same. You can't have more than 2 repeating numbers, okay? How would you try something like this? And I encourage you to pause the video right now and give this one a go. Well, in this situation, what we would say is that probably at least for me, the way I would think about this, the most efficient way would be to just come up with all the combinations or all the combos, and from that, subtract, can you think about it? we want to subtract all the three number, or I should say three of the same number combinations. Three of the same number combinations. Right? So what we want to do is we want to find all the combinations and subtract from them all the 111s, all the 222s, or the 333s, all the combinations that have all three numbers the same. So if you remove those, literally remove those from the equation, all you're left with are the combinations where you could have maybe at most two numbers the same. So what would that look like? Well, all the combinations, well, that would be, we said 64,000. And if you have, how many combinations are there where all the numbers are the same? Well, you would have to have 40 of those, the 111s, 222s, or I should probably could even start at 000. So you subtract 40 from that. So you have a total of 63,960 combinations in this problem. Okay. All right, let's try another problem. How many different 7-digit phone numbers can be made if the first two digits cannot be 0 or 1? Okay. I know you're not really used to typing in numbers anymore in your phone. You have everyone on kind of speed dial or just save contacts. But if you remember the days when we actually used to enter phone numbers in, all right, so let's think about that. How many different 7-digit phone numbers can be made if the first two digits cannot be 0 or 1? And repeats are going to be okay here. All right, so let's look through this. So I'm going to go ahead and I'm just going to create 7 spots for my 7 digits. Now in the first spot, okay, I can choose any number as long as it's not 0 or 1. So what does that leave me? It leaves me with the numbers 2 through 9. That's a total of 8 numbers that are possible there. And the problem does specify that repeats are okay. So in the second spot, as long as I don't choose 0 or 1, I can choose 8 numbers here. And I'm multiplying all of these because I'm using the fundamental counting principle. Now, when we move to the third spot or the third digit, here now we can choose any number that we want, as long as it's obviously a single digit number, right? So any single digit number. So now I've got a total of 10 possibilities, all the numbers from 0 through 9, and so on and so forth. All these others, there are no conditions placed on them, so I can do that. So that's going to give me a total of 64. How many zeros are there? 5. So we've got a total of 6,400,000 possible phone numbers that can be generated as long as the first two digits are neither 0 or 1. Okay, let's try one more example before we start talking about permutations. So let's look at a license plate, and it has one number and then 3 letters and then 3 numbers. Okay, this is typically how it's done in the state of California, if I'm not mistaken. But we're going to have a total of 7 spots. So let me just go ahead and write those out. And in these 7 spots, in the first spot, you can have one number. Then in the next 3 spots, you have to use 3 letters. And then in the final 3 spots, you've got to have 3 numbers. And repeats are okay here. So pause this video and go ahead and try this problem on your own first. Well, in the first spot, if you can have a number, then we just said from the previous round, that means we have 10 different possibilities there. Now, if I'm going to choose a letter, how many letters are in the alphabet? Hopefully you know that. That's 26. That means in the next spot, since we can use the same letter again, we're going to write 26 again, and then 26 again. And in the final 3 spots, since we're back to numbers, we would then write 10 times 10 times 10. So multiply all those together, you get 175,760,000 possible plates. And we'll go ahead and box that. Okay? So that's the fundamental counting principle. Again, when we want to quickly and efficiently find a way of finding all the different ways that one event and another event can occur, we would simply calculate those number of ways, m and n, and then multiply them together.